Okay, hey folks, we're going to talk about some stuff that I hope is familiar to you all. Valence bond theory and sigma bonds and pi bonds. So we're going to talk about the quantum mechanics basis on these types of bonds and where they come from. So in the development of valence bond theory, we will use the separation of variables technique, where we're going to make this wave function out of valence electrons. So we can start with H2, which only contains one electron in each hydrogen, right? So that's the only one we have to choose from. And we can build up that wave function by making this separation of variables of the hydrogen 1s electron wave function for one of them, and an identical hydrogen 1s wave function for the other. And if we look at this graph right here, this A1 we could think about as just a shorthand notation for saying this hydrogen 1s electron, where A gives me atom A and 1 is electron number 1. So atom B is given by the following. And of course, we could call that then electron number 2. So now on this picture here, this decaying exponential that we see right there, so that is proportional to e to the negative r divided by the Bohr radius, right? If you recall, that was the hydrogen 1s wave function. And so we can see in the positive r space, it decays out as such. And in the negative r space, it decays in a similar way, giving us this spherical 1s wave function, or really orbital, right? And then you can see we have a neighboring one as well. And where these have mutual overlap, so I'm going to point to this area and refer to that as overlap. We're going to hear that term a lot. We would expect them to get constructive interference owing to enhanced electron density in the internuclear zone, which will make our chemical bond. Now, of course, Pauling tells us, or really I should say Heisenberg tells us, we don't know which is which with arbitrary precision. So then Pauling tells us we need to switch those. And if we do switch those, we get only a handful of acceptable results. So the idea here is we're going to look at a potential basis set where we'll say, let's see, where did my thing go? Here we go. We'll say psi H2 equals A1B2 plus or minus, because remember, both are possible, times A2B1. Well, as we'll see, I'll do a little bit of foreshadowing and note that the positive state, the plus state, will refer to constructive interference, and that will give us bonding. So positive equals bonding. And the negative gives us destructive interference, which is not quite fully described in valence bond theory. It's more developed in molecular orbital theory. But all the same, we should recognize that as anti-bonding. So no bond at all. So putting that together here, I've indicated the positive state, A1B2 plus A2B1. And we also have to remember to use the acceptable spin wave function that describes a singlet state, right? So we can't make a bond out of a triplet state, two unpaired electrons. We've got to bond them up. And specifically, we call this type of bond a sigma bond. So a sigma bond, by definition, has shared electron density within the internuclear zone, and it is cylindrically symmetrical about the z-axis. So if I'm looking at this kind of picture head on here and making a coordinate system, my x-axis will be out there, my y-axis will be out there, and my z-axis will be coming in and out of the plane indicated by the thick or dashed wedges. So our z-axis will be our internuclear axis that is described by the sigma bond. Okay, so what if we don't have this cylindrical symmetry made by s orbitals? Is there another way to do that? And yes, there is. We could do that with pz orbitals. So if I look at nitrogen, and specifically its valence electrons, we see nitrogen has 3 valence electrons, px, py, and pz. And we can only make this sigma bond about the z-axis. So once again, if I draw this coordinate system here, there is my z, perhaps that is my y, and that is my x, right? And we would have an identical coordinate system on this other nitrogen atom. So now when we get those close to each other and get this overlap, this enhanced electron density in the internuclear zone, we also make this cylindrically symmetrical orbital about the z-axis. So this is still a sigma bond. So we can make sigma bonds from s orbitals, or we can make sigma bonds from pz orbitals. And so now, of course, it makes sense to think about what can happen with the px and the py. And nitrogen gives us a good example because it has 1 in each. We still have to use this wave function given to us by Pauli, where we have this singlet state, the sigma minus 1, 2 state. But now what we start creating are enhanced electron densities above and outside, above and below, let's say, the internuclear axis. So for example, if I look at, I'm going to highlight this orbital right here. So we'll say the plus and the minus. So we could arbitrarily define that as px. And you can see we've got another identical px orbital on this neighboring atom. So I'm kind of like trying to indicate here which ones are which. So that would be px. So now you can see as these get close, we could make a singlet state. So we could make a chemical bond away from the internuclear axis. And we would call that, or we do call that, a pi bond. So now in the case of nitrogen, you might notice that it has another dimension that we can do that on. So we've got also the py. So, and of course that's arbitrary. I could have called the px the py and the py the px. But what's important to note is that they are not the z-axis. Okay. So now you can see we could make another singlet state with those particular orbitals as well. So that would be py and py. And so thus we would get 2 pi bonds out of this thing. One from the x and one from the y. And you can see this picture right here is just reminding us that we have this nodal plane with different phases, and it's those different phases and their constructive interference that makes this possible. Okay, folks, we'll keep going down this rabbit hole in the next video.